Hey everybody, this is Larry. This is me going Q4 of the weekly contest 263, second minimum time to reach destination. So this one is tricky. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem. Also, there are a lot of cool, smart, nerdy people like me on my Discord, so we'll come check it out and hang out. Yeah. Anyway, for this one, it is the shortest path problem. So, I don't know how I want to describe this one. There are definitely a lot of possible ways to go about this one. And to be honest, I'm not gonna lie, frankly, when I first submitted this problem, and you can watch my reaction when I was submitting it, I wasn't sure that I had the right answer. I was willing to submit to get a wrong answer to kind of get a test case to disprove my greedy solution. Greedy problems, as a lot of people struggle with, it's very hard, at least for me especially, or at least it's not hard to implement because it's just greedy, right? But it's very hard because you have to prove the answer correct, or you don't have to, but you have, but ideally at some point, if not during the contest. But yeah, that said, many shortest path algorithms are greedy problems or greedy algorithms, right? For example, Dijkstra, breadth first search, all these things are greedy, right? So that being said, yeah, I think the other thing I would say is that I have solved second shortest path problems, so I have an idea of how to think about it. Though that said, I don't think I did it quite that way this time. I think this time I didn't invent, but I kind of reinvent. I don't think that's in reinvent, but you know what I mean. But I didn't come up with it as in I invented it, but I came up with this thing to kind of rethink about how to do this. I'm not sure that this is the best running time or way, but that this is the way that I did it, and it is using Dijkstra. I think this is correct. Or mostly correct. Like, I was not 100% confident, but I had good reason. I just thought that maybe I also made a mistake somewhere. But the thing with Dijkstra, and these are the things that if you really study about these algorithms, maybe you can remember it, maybe you don't. But the thing with Dijkstra and A* search, maybe more specifically, is that as long as your function is pessimistic, you will get the answer, right? And this particular problem, the difference between this one and a quote-unquote regular second shortest path problem is that this has to be the second uniquely shortest path, right? What I mean by that is that if there are three ways to get from A to B, and the second shortest, there are a lot of problems where the second shortest doesn't have to be unique, but in this problem it does, which kind of add some questions in my mind whether I'm doing it correctly. But okay, that being said, let me go, and also, so I'm just talking about the second minimum time part, but I didn't even talk about the green to red part, but I think that part's not actually that bad. We can go over it as we go over the shortest path, because every other part of this is just part of the shortest path algorithm. Okay. So the way that I thought about it is basically create a second, I think technically it's called dual graph, but basically what I do is I create a second possible graph where for every node in the existing graph, I create a second node. Let me actually draw some stuff here, maybe to kind of illustrate it a little bit better. So the idea, let me actually show it on screen. That will also be good. So the idea is that, okay, let's say I have something simple for now. I have something like, this goes here, goes here, and then I don't know, right? Fine, right? So here, what I did is that I create a secondary graph, where, this is the that is a terrible line. So I create a dual graph, and I don't know that this is the best way, but this is the way that I did it. People might have a different way of doing it. So actually, let me just copy and paste. I can copy and paste if we're doing it. What the hey? What the hey? Okay. So yeah, so basically you can, imagine that, now we convert this to two graphs, where this is where I'm just changing colors. Where this one, I did not change colors. Where this one, it gives us the shortest path, and this is the second shortest path one, right? And then we draw additional lines where here, for every line here, this also goes to here, this also goes to here, this also goes to here, and this also goes to here. So basically for every, and the reason is that, for example, this, keep on changing colors, but it's not changing. Okay. So for example, like for this node and this node, because there's an edge between these two, on the second shortest path, we create a node that connects them, because now there is a possible edge there. That's basically my idea. And then the best answer then is going to be, or your answer is going to be at this node. Basically, your answer is going to be, why does it keep on not changing the answer, or changing the colors in it? Okay, so your answer is going to be on this node, because that's this graph is going to contain your second best answer, right? So that's basically the visualization behind it. We'll go over in code, and we'll go over in more detail. Don't you worry. But yeah, so basically, yeah, and we'll go over the red light, green light thing as well. Maybe someone has watched Squid Game. That's, maybe I did too. But yeah, so first of all, we construct the edge list. I think this is pretty standard. So I'm not going to go over it too deeply. At least if you have done enough Leetcode, this is relatively standard. They give you an edge list, and you convert it to an adjacency list, right? So that it's easier to look up the edges. I just kind of pre-calculate change times 2 for reasons that we'll talk about later. So here we construct the distance for, like we said, we create for every node 2 times n of that node. We start from the 0. I converted these to 0 index, and then we start at the 0 where we gets the shortest path to 0. We set that to 0, right? So this is d current and t. D is equal to I guess the distance or time to get here to this state. Current is equal to current node. T is equal to the t shortest path, 0 indexed, right? So yeah, so that's basically the idea, and then the code kind of follows from that. So this is Dijkstra. This is just so that we don't do any extra work. It's not a big deal, because at most you're gonna relax this over, But basically, my Dijkstra algorithm is going to be v log e time, or but of course this is just, for y is equal to adverse v square. So that means that this is over v log v square, which is of course, you could take the 2 to the beginning, which is over v log v. So this is basically the same, except for, I guess it's roughly speaking 2 times slower, but it's not that big of a deal. But yeah, this is standard Dijkstra. Did I spell that right? Hope I spelled that right. Nope. If I is that how I spell it? I think that's right. Maybe not. I don't know. Really bad with spelling right now. Okay. But yeah, so that's gonna be fast enough. For n is equal to 10 to the 4th. There could be more edges, but I guess not actually. But yeah. So we skip this so that we can add more edges into the heap or more things into the heap without recognizing it. This is just standard Dijkstra stuff. So this is the red light, handling red light, green light, right? So basically, So the way that I think about how I structure this is that you can arrive at any time, right? The destination, you can arrive at any time. So this T would be the shortest thing when you get there. But you cannot always leave, right? So the question is, when can I leave this current state? So basically, I two is change times 2 because we separate, there's a segment and then another segment, right? So this is going to be of length change, and then the entire thing is going to be of length change 2. And so basically the idea is that we have this thing but repeating. So this is red light, green light, green light, red light. So maybe we can convert this into whatever. I'll just write G in the beginning so you see. And then this keeps on repeating forever, right? Dot dot dot. So then the question is, are we in the green section or in the red section? So that's basically what this thing tries to do. Basically, we take the mod of change 2 because this, this repeats in change 2 kind of way. If we do it in that way, then if this is in the first half, then we're good because this is green, so then we don't have to change anything. If this is in the red half, what do? Well, if this is in the case, then this is just a formula to make it, to add it to the next one. I derived it myself during the contest, so it's not like it's a formula that you need to know. And I had to think about whether there's like a 0 case and other edge cases, so you have to be really careful. But the idea here is that basically, let's say I'm here, so then I subtract everything to get it to the first green, and then I add it to get to the next green. That's basically the idea. So this gets me to the previous green, and this gets me to the next green. And then now, this D, which is the time, the current time, the distance that we based off will be from here. So then now we're here and we're leaving at this moment plus time, right? So then here, this is the different test, not test cases, the different transitional cases here. Yeah, so this is the different cases. For every edge in this edge list, in this adjacency list, we check whether, okay, if we leave from here now, is this the shortest time, right? If this is the shortest time, then we update it by, kind of just pushing things over, right? Because now, the second shortest time to V, we set it to the previous shortest time. So basically just pushing things over, and then we kind of put this in the heap to kind of relax that just in case we need it, and then we update the shortest time, put it in the heap, right? Otherwise, that means that this is not the shortest time, but is it the second shortest time, right? So the thing that I was a little bit tricked or required more thought about was this tiebreaker thing, because this is the second unique minimal time and not just the second time. So I have to do this thing where, okay, if this is Leetcode, we actually get to skip it, because that means that that means that if we update this time, then these two things would be equal, and we don't want that. So that's why we skip it in this case. Otherwise, we can update the second shortest time directly by pushing in the heap. So other than this like logic here, everything is standard Dijkstra. So yeah. So I'm not gonna go over it too deeply, but this is, for me, this is the key part of this problem in terms of implementation. And because here it makes sense, right? It's just about manually maintaining and pushing the second best out and so forth, and put it back in the heap, because we might get that, we might use that as the second closest thing in the future, right? Yeah. There is actually a case that I didn't explicitly do, which is that technically speaking, you cannot reach the first, like if we bring back the diagram for a second, technically you cannot, you can, at least in code, that's what I did anyway. There's no way for this to kind of go backwards in this direction, but the thing is that it doesn't matter. The reason why I don't check it, or I don't need to check for it explicitly, is because that would never yield a shortest path, because by definition, the first shortest path will be shorter and would have gotten to that first shortest path node quicker. So that's one thing that I actually just noticed now, and thankfully that didn't come to bite me. But that's because, yeah, greedy has these probably sometimes. Anyway, that's all I have for this one. Let me know what you think. And you can watch me sub live in the contest next. I'm trying to make this a little bit smaller so you can see it on one screen, but maybe I'll just do here. Here's I'll make it slightly bigger so you can see it anyway. Here's the first half, and here's the second half. But as you can see, this is mostly standard Dijkstra, and some of this logic with the greedy and stuff like that will, to be frank, it's just because I've solved similar problems with the second shortest path. So with the only kind of variation is on this thing where where's the second unique versus the second shortest. So anyway, that's all I have for this one. You could watch me solve it live during the contest next. This is a hard one to get right exactly. I even did a change. Okay, that's not so bad, but it is confusing as hell. How do I handle this? Dual graphs? Maybe. Okay, let's think about it. Is that true? I feel like I'm missing something, but no one got it yet. That's surprising, actually. That's not true. Time. Yep. See. If so, then here we have to adjust this to be the leaving time. Closing time. basically the current time then is now a multiple of change times 2. Change is weird. No. Then we're good. Then this is green. Otherwise, if this is the case, then we go to the next one. So then that means, oh, I messed it up. If this is the case, then we add, we make it so that this is the next change of 2. So this is the 4. Unless this is 0, right? No, that's not true. Because can it be 0? No, because it's bigger than it by definition. Okay, maybe. I have to double check this one. Yeah, and this is 0, but this cannot be 0 because, okay, I think this is good. I don't think this is right, but I'm going to YOLO. It's a little too early to kind of get a wrong answer, get the test case, and then figure it out. Okay, maybe not then. Yeah. Hey, thanks for watching it up to now. Yeah. Have a great time. Hit the like button. Hit the subscribe button. Join me on Discord. Talk about this problem, other problems, this contest, whatever you like to do. And yeah, stay good, stay healthy. to good mental health. Have a great rest of the weekend. Have a great rest of the week. We'll do the daily prompts. We'll see you later, and I'll see. And bye bye.